Hello and welcome everyone. This is Gursimran Singh. In this session, we will discuss cryptographic techniques. Before discussing cryptographic techniques, let's have a quick look on crypto terminologies. The basic terminology of crypto includes number 1, cryptology, the art and science of making and breaking secret codes. Cryptography, the making of secret codes. Cryptanalysis, the breaking of secret codes. Crypto, a synonym for any or all of the mentioned before, where the precise meaning should be clear from context. A cipher or crypt system is used to encrypt data. The original unencrypted data is known as plain text, and the result of encryption is ciphertext. We decrypt the ciphertext to recover the original plain text. A key is used to configure a crypto system for encryption and decryption. Cryptography techniques can be broadly categorized into 3 categories. Number 1, symmetric key cryptography. Number 2, asymmetric key cryptography. And number 3, hash functions. Now let's start our discussion with first cryptographic technique, that is symmetric key cryptography. First, let's have a quick look at symmetric cipher model. Figure represents the concept of symmetric cipher model. It has 5 main components, that are number 1, plain text. This is the original understandable message or data that is fed into the algorithm as input. Number 2, encryption algorithm. The encryption algorithm performs various substitutions, transformations on the plain text. Secret key. The secret key is also input to the encryption algorithm. The key is a value independent of the plain text and the algorithm. The algorithm will produce a different output depending upon the specific key being used at the time. The exact substitutions and transformations performed by the algorithm depend upon the key. Number 4, ciphertext. This is the scrambled message produced as output. It depends on the plain text and the secret key. For a given message, 2 different keys will produce 2 different ciphertexts. The ciphertext is an apparently random stream of data, and as it stands, it is unintelligible. Number 5, decryption algorithm. This is essentially the encryption algorithm run in reverse. It takes the ciphertext as input and secret key produces the original plain text. In this model, plain text is used as input. We convert the plain text into ciphertext by using encryption algorithm key. On the receiver side, ciphertext is converted into plain text by using decryption algorithm and key. In symmetric cryptography, sender and receiver share the same secret key. There are 2 requirements for secure use of conventional encryption. Number 1, we need a strong encryption algorithm. This requirement is usually stated in a stronger form. The opponent should be unable to decrypt ciphertext or discover the key, even if he or she is in possession of a number of ciphertexts together with the plain text that produced each ciphertext. Number 2, sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure. If someone can discover the key and knows the algorithm, all communication using the key is readable. On the sender side, with the message P and the encryption key K as input, the encryption algorithm forms the ciphertext C. We can write it as ciphertext is equal to the encryption function of key and plain text. On receiver side, decryption can be performed as plain text is equal to decryption function of key and ciphertext. Now, where P is equal to plain text, K is equal to key and C is equal to ciphertext. The symmetric cryptographic techniques can be further divided into classical and modern symmetric cryptographic techniques. First of all, we will discuss the classical symmetric cryptographic techniques. Now, in classical symmetric cryptographic techniques, we examine classic ciphers, each of which illustrate a feature that is relevant to modern crypto systems. First, we will discuss the simple substitution, which is one of the older cipher system dating back at least 2000 years and one that is good for illustrating some basic attacks also. Substitution cipher techniques, it includes letters of plain text that are replaced by other letters. If the plain text is viewed as a sequence of bits, then the substitution involves replacing plain text bit patterns with cipher text bit patterns, as shown in the figure. To write down a key for the substitution cipher, we first write down the alphabet and then a permutation of the alphabet directly below it. This mapping gives the substitution we make between the plain text and the cipher text. Encryption involves replacing each letter in the top row by its value in the bottom row. Decryption involves first looking for the letter in the bottom row and then seeking which letter is top row maps to it. Hence, the plain text word hello, that is HELLO, would encrypt the cipher text ESVVJ if we use the substitution given before. The number of possible keys is equal to the total number of permutations on 26 letters. Substitution cipher can be of two types, that is classical substitution cipher, monoalphabetic and polyalphabetic. If the substitution is done uniformly, this is called a monoalphabetical cipher or simple substitution cipher. In simple words, we can say in monoalphabetic substitution, an alphabet is replaced with the same alphabet in the entire text. In polyalphabetic substitution, different substitutions are made depending upon where in the plain text the symbol occurs. It means the same character can be replaced with different characters in the text. For example, A can be replaced with D and B in different places of the occurrence. The second classical substitution technique is transposition technique. The substitution cipher involves the substitution of ciphertext symbol for a plain text symbol. A very different kind of mapping is achieved by performing some sort of permutation on the plain text letters. This technique is referred to as transposition ciphers. The simplest such cipher is the rail fence technique, in which the plain text is written down as a sequence of diagonals and then read off as a sequence of rows. For example, as you can observe in the figure, encipher the message "Meet me after the toga party" with a rail fence of depth 2. We can write it as, you can observe in the figure, the encrypted message is MEMATRYETEFETOAA and T. The sort of thing would be trivial to cryptoanalyze. A more complex scheme is to write the message in a rectangle row by row and read the message of column by column, but permute the order of the columns. The order of the columns then becomes the key to the algorithm. Now, let us discuss modern symmetric cryptographic techniques. Modern symmetric cryptographic techniques can be divided into two categories: stream and block ciphers. Stream ciphers. The key stream is the XORed with plain text P to produce ciphertext C through the magic of XOR. The same key stream is used to recover the plain text P from the ciphertext C. The function of a stream cipher can be viewed simply as stream cipher K is equal to S, where K is the key and S is the resulting key stream. Remember, the key stream is not ciphertext, but instead simply a string of the bits. Now, given a key stream S is equal to S0, S1, S2 up to N, and plain text P is equal to P0, P1, P2 up to Pn, we generate the ciphertext C is equal to C1, C2, C3 up to n by XORing the corresponding bits. As you can observe in the figure, C0 is equal to P0 XOR S0, C1 is equal to P1 XOR S1, C2 equal to P2 XOR S2 and so on. To decrypt ciphertext C, the key stream S is again used, that is plaintext P0 is equal to C0 XOR S0, P1 is equal to C1 XOR S1 and plaintext P2 is equal to C2 XOR S2 and so on, provided that both the sender and receiver have the same stream cipher algorithm and that both know the key K. The resulting cipher is not probably secure. So, we have traded probable security for practicality. The examples of stream ciphers are A5 by 1 and RC4. Now, let us discuss the block ciphers. A block cipher splits the plaintext into fixed size of blocks and generate fixed size blocks of ciphertext. In most designs, the ciphertext is obtained from the plaintext by iterating a function f over some numbers of round. The function f, which depends on the output of previous round and the key k, is known as the round function, not because of its shape, but because it is supplied over multiple rounds. The design goals for block ciphers are security and efficiency. It is not too difficult to develop a secure block cipher or an efficient block cipher, but to design one that is secure and efficient requires a high form of cryptographer's art. Figure illustrates the logic of a general substitution cipher. For n is equal to 4, a 4-bit input produces one of 16 possible input states, which is mapped by the substitution cipher into a unique one of 16 possible output states, each of which is represented by 4 ciphertext bits. The encryption and decryption mapping can be defined by a tabulation. This is the most general form of block cipher and can be used to define any reversible mapping between plaintext and ciphertext. Feastel refers to this as the idea block cipher because it allows for the maximum number of possible encryption mapping from the plaintext block. There is a practical problem with the ideal block cipher. If a small block size such as n equal to 4 is used, then system is equivalent to a classical substitution cipher. Such systems are vulnerable to a statistical analysis of the plaintext. This weakness is not inherent in the use of a substitution cipher, but rather results from the use of a small block size. If n is sufficiently large, an arbitrary reversible substitution between plaintext and ciphertext is allowed. Then the statistical characteristics of source plaintext are masked to such an extent this type of cryptanalysis is infeasible. An arbitrary reversible substitution cipher, the ideal block cipher for a large block size, is not practical. An implementation and performance point of view, for such a transformation, the mapping itself constitutes the key. In considering these difficulties, Feastel points out that what is needed is an approximation to the ideal block cipher system for large n, built up out of components that are easily resizable. But before turning the Feastel's approach, let us make one other observation. We could use a general block substitution cipher, but to make its implementation tractable, confine ourselves to a subset of the possible reversible mappings. For example, suppose we define the mapping in terms of a set of linear equations. In the case of n equal to 4, we have the formula as shown in the figure, where the xi are the 4 binary digits of the plaintext block, the yi are the 4 binary digits of the ciphertext block, the kij are the binary coefficients, and arithmetic is mode 2. The key size is just n raised power 2 in this case 16 bits. The danger with the kind of formulation is that it may be vulnerable to cryptanalysis by an attacker that is aware of the structure of the algorithm. In this example, what we have is essentially the Hill cipher applied to binary data rather than the characters. As a simple linear system such as this is quite vulnerable. Let us discuss the Feistel cipher in brief. A Feistel cipher named after block cipher pioneer Horst Feistel is a general cipher design principle, not a specific cipher. In a Feistel cipher, the plain text block P is split into left and right halves, whereas P is equal to L0 and R0, and for each round I is equal to 1 to n. New left and right halves are computed according to the rules as shown in the figure, where Ki is the subkey for round I. The subkey is derived from the key K according to a specified key schedule algorithm. As you can observe in the figure, the ciphertext C is the output of the final round, namely C is equal to Ln and Rn. Instead of trying to memorize equation 1 and 2, it is much easier to simply remember how each round of a Feistel cipher works. Note that equation 1 tells us the new left half is the old right half. On the other hand, equation 2 says that new right half is the old left half XORed with a function of the old right half and the key. Of course, it is necessary to be able to decrypt the ciphertext. The beauty of the Feistel cipher is that we can decrypt regardless of the particular round function f. Thanks to the magic of the XOR, we can solve equation 1 and 2 for Ri to 1 and Li minus 1 respectively, which follows us to run the process backwards. This is for I is equal to n minus 1 up to 1. The decryption rule is as shown in the figure. The final round of the decryption process is the plain text P is equal to L0 and R0 as desired. Again, any round function f will work in Feistel cipher provided that the output of f produces the correct number of bits. It is particularly nice that there is no requirement that the function f be invertible. However, a Feistel cipher will not be secure for all possible choices of f. For example, the round function is as shown in the figure. It is a legal round function since we can encrypt and decrypt with the f. Note that all questions about the security of the Feistel cipher boil down to question about the round function of the key schedule. The key schedule is usually not a major issue, so most of the analysis can be focused on f. Other examples of the block ciphers are DES, that is Digital Encryption Standard, Triple Digital Encryption Standard, and AES, that is Advanced Encryption Standards. Now, we will discuss the asymmetric key ciphers. Symmetric and asymmetric key ciphers will exist in parallel. Actually, they are complements of each other. The advantage of one can compensate for the disadvantage of the other. The conceptual difference between two systems are based on how these systems keep a secret. In symmetric key cryptography, the secret key must be shared between two persons. In asymmetric cryptography, the secret key is personal, that is unshared. Each person creates and keeps his or her own secret. In a community of n people, n into n minus 1 by 2 shared secrets are needed for symmetric key cryptography. Only n personal secrets are needed in asymmetric key cryptography. For a community with population of 1 million, symmetric key cryptography would require half a billion shared secrets. Asymmetric key cryptography would require 1 million personal secrets. There are some other aspects of security besides the encipherment that need asymmetric key cryptography. These include authentication and digital signatures. Now, whenever an application is based upon the personal secret, we need to use the asymmetric key cryptography, whereas symmetric key cryptography is based upon substitution and permutation of symbols. It can be characters or bits. Asymmetric key cryptography is based on applying mathematical function to numbers. In symmetric key cryptography, the plain text and ciphertext are thought as a combination of symbols. Encryption and decryption permute these symbols or substitute a symbol for another. In asymmetric key cryptography, the plain text and ciphertext are numbers. Encryption and decryptions are mathematical functions that are applied to numbers to create other numbers. Following figure represents the concept of asymmetric key cipher or public key ciphers. Now, let us discuss some of the concepts of the asymmetric key cryptography. The first one is keys. Asymmetric key cryptography uses two separate keys, one private and one public. If encryption and decryptions are thought of as locking and unlocking padlocks with keys, then the padlocks that is locked with the public key can be unlocked only with the corresponding private key. Figure shows that if Alice locks the padlock with Bob's public key, then only Bob's private key can unlock it. Now, the second concept is plain text or ciphertext. Unlike in symmetric key cryptography, plain text and ciphertext are treated as integer in asymmetric cryptography. The message must be encoded as an integer or a set of integers. Before encryption, the integer or the set of integers must be decoded into the message after decryption. Asymmetric key cryptography is normally used to encrypt or decrypt small pieces of the information, such as the cipher key for symmetric key cryptography. In other words, asymmetric key cryptography normally is used for secondary goals instead of message encipherments. However, these secondary goals plays a very important role in cryptography. Now, the third concept is encryption and decryption. Encryption and decryption in asymmetric key cryptography are mathematical functions applied over the numbers representing the plain and ciphertext. The ciphertext can be thought of as C is equal to f function of k public key and plain text. The plain text can be thought of as P is equal to G k is private then ciphertext. The decryption function f is used only for encryption. The decryption function G is used only for decryption. Need for the both. There is a very important fact that is sometimes misunderstood. The advent of asymmetric cryptography does not eliminate the need for symmetric cryptography. The reason is that asymmetric key cryptography, which uses mathematical functions for encryption and decryption, is much slower than the symmetric key cryptography. For encipherment of large messages, symmetric key cryptography is still needed. On the other hand, speed of symmetric key cryptography does not eliminate the need for asymmetric key cryptography. Asymmetric key cryptography is still needed for authentication, digital signatures and secret key exchange. This means that to able to use all services of security today, we need both symmetric key and asymmetric key cryptography. One complements the other, simple. Now, let us discuss the RSA. Although there are several asymmetric key crypto systems, one of the common public key algorithm is the RSA crypto system, named from its inventors Rivest, Shamir and Edelman. The figure represents the general procedure of the RSA crypto system. RSA uses two exponents E and D, where E is public and D is private. Suppose P is the plain text and C is the ciphertext. Sender uses C is equal to PE mod N to create ciphertext C from plain text P. A receiver uses P is equal to CD mod N to retrieve the plain text sent by the sender. The modulus N, a very large number, is created during the key generation process. As shown in the figure, receiver choose two large numbers P and q and calculates n equal to p and q and f is equal to p minus 1 into q minus 1. Receiver then select E and D such as E into D mod f is equal to 1. Receiver advertise E and N to the community as the public keys. Receiver keeps D as the secret key, including can encrypt a message and send the ciphertext using C is equal to PE. Only receiver can decrypt the message using P is equal to CD. An intruder such cannot decrypt the message if P and Q are very large numbers because he don't know the D, that is the private key. Now the hash functions. A cryptographic hash functions takes a message of arbitrary length and creates a message digest of fixed length. All cryptographic hash functions need to create a fixed size digest out of a variable size message. Creating such a function is best accomplished using iterations. Instead of using a hash function with variable size input, a function with fixed size input is created and is used as necessary numbers of times. The fixed size input function is referred to as compression function. It compresses an n bit string to create an m bit string where n is normally greater than m. The scheme is referred to as an iterated cryptographic hash functions. Several hash algorithms are designed by Ron Rivest. These are referred to as MD2, MD4, MD5, where MD stands for message digest. The last version, message digest 5, is strong version of message digest 4 that divides the message into blocks of 512 bits and create a 128 bit digest. It turns out the message digest of size 128 bits is to be small to resist attack. The secure hash algorithm SHA is standard that was developed by the National Institute of Standards and Technology NIST. SHA has gone through several versions. So, in this session we discussed cryptographic techniques that can be broadly divided into symmetric key cryptography, asymmetric key cryptography, and lastly discussed hash functions. Each technique have their own pros and cons, but in real world these techniques exist in parallel and helping in keeping the information secure on the public networks. So, that's it for today's session. Thank you for watching.